Okay, so I'm assuming that you guys can see my screen, correct?
Yes, we can see it.
Perfect. So as Michael mentioned today, I would like to present UNETR, which is Transformers for 3D Medical Image Segmentation. And my name is Ali Hatamizadeh. I'm part of the NVIDIA DLMed. And in this work, we have also other collaborators and colleagues whose names are listed here. So recently, transformer-based models have gained lots of attraction in both the natural language processing and computer vision field. And you can attribute this success due to the exceptional capability of these models in learning pretext tasks or their scalability for large scale training or pre-training, and then their good performance in modeling long-range spatial dependencies. And here, I have an image of the original vision transformer model, which was proposed last year. So the idea is that instead of processing the image, just as in convolutional neural networks, by applying a kernel-sized, a limited kernel CNN to the image itself. So you want to actually break the image into patches and then project the patches into some sort of embeddings, and then the embeddings are processed within the transformer encoder. And then at the end, you can actually apply a multi-layer perceptron head to make some classification, or also you can use the features for other downstream tasks. So this was the idea of the vision transformers, and they have already achieved a state-of-the-art performance on multiple data sets. So based on this idea, so we present the UNET transformers, or in short, UNETR. So here, just like the VEET model, so we want to actually reformulate the task of the 3D segmentation as 1D sequence-to-sequence predictions using these token embeddings. And then basically we use some self-attention modules in each of these transformer encoder layers to learn a weighted sum of the values that come from the previous hidden layers. And then we basically connect the transformer encoder to a CNN-based decoder to make the final segmentation output. So here I have a brief overview of our methodology, and specifically I want to basically emphasize on the fact that our method directly utilizes 3D patches, which is actually important in the context of this medical image segmentation. And so our model actually achieves the state-of-the-art performance on the multi-organ segmentation data set. So this data set is known as Synapse, but the correct name of this data set is BTCV, but here I put the name Synapse so that people can also relate to what they know about the Synapse data set itself. So getting a little bit more into the nitty-gritty of the details. So here you can see that we actually can feed in basically 3D inputs with multi-modal information, such as these brain images. So they have 4 modalities, and then you directly input this into our volumetric linear projection layer, and then we project this into some embedding space, and then the embeddings are fed into 12 layers of transformer encoders. And then, so at every 3 steps of the layers, so we extract the features and then we feed them into a CNN-based decoder, which is in this case a UNET decoder via escape connections. And at the end, so we use these extracted features to actually make the final predictions, as you can see here. And then to do this, so just following the nomenclature of these transformer models, we use a desired, let's say, image resolution or patch resolution of the P, in this case, 16 by 16 by 16, and then we break the image into non-overlapping patches, and then use a k-dimensional embedding space to basically project the extracted patches. We also add a positional encoding layer for which we want to retain some spatial information. And then within the transformer layers, so each basically layer contains of 2 submodules. So one is the multi-head self-attention, and then the other one is the multi-layer perceptron, as shown here. And then we also use a layer normalization as the input to these MSA and MLP submodules. And so the MSA layers itself, so it basically consists of n parallel self-attention heads. And you can think about a self-attention head as basically a layer that learns a mapping between query and key and values within a sequence Z. And then we do this by basically measuring the similarity between the two elements in the Z sequence, and then the corresponding key and value pairs. And then we simply just multiply these attention rates to the value, and then we concatenate them and multiply that by a matrix, which is some learnable weights that allow us to relate these layers together. So this is the entire idea of the multi-head self-attention, which is used in our work. And basically here, I want to show you some results from the experiments. So first, results on the BTCV public leaderboard. So this is a multi-organ segmentation task. So there are 14 organs, and so the data set is actually publicly available, but this leaderboard, the labels are not available. So you have to make submissions to get these results. And we actually made submissions not only for our model, but also for other competing methods, such as NNUNET, which has shown promising results in multiple segmentation tasks, and also some other transformer-based segmentation models, such as TransUnit, SETR, and QUALITATIVE. And you can see that, so in these results, the one on top is actually using the standard competition, which means that you only can use the data set that is released by the challenge organizer. And the one on the bottom are the free competition, which is you cannot use any sort of source of data that you have. And you can see that in both of these competition tracks, we outperform the existing methods, but by quite a large margin, and then establish our method as the current state of the art on the BTCV dataset. We also tested the performance of our model on two tasks from the MSC dataset. So one is the brain tumor segmentation using the MR modality, and then the other one is the spleen segmentation. And here again, we also added some other works such as TransBTS, which is a transformer network, but just for brain segmentation, just as a comparison. And we see that even in these two tasks, we outperform the competing methods by a large margin in both using the DICE and Hausdorff distance matrix. So looking at some qualitative results on the multi-organ segmentation, we see better performance, especially with some of the organs such as adrenal glands. So these networks, most of them fail actually to capture the long-range dependencies that are needed to segment some of these specific organs. And then we show that our model actually outperforms both TransUnit and NNUnit, even in these visual comparisons. And same story here for the brain tumor segmentation. So we validated the basically efficacy of our model by also showing these qualitative results. As far as the model complexity is concerned, so we show that first of all, our model actually has the least number of the gigaflops in comparison to the competing approaches, such as NNUnit and TransUnit, and also the second fastest model only behind NNUnit. And you can see that there is a large discrepancy between our model and TransUnit. And this is mainly due to the fact that TransUnit is actually a 2D segmentation model. So it needs to process slides one by one, whereas our model is a fully 3D model. So you can actually you can actually obtain a full inference in a one shot, right? So you basically save on going through every slice. The same also for the setter. So we think that also our model is a reasonably sized model in terms of the number of the parameters, as also shown here. So in conclusion, so we propose UNETR, which is a novel transformer-based segmentation model for medical image semantic segmentation. We have achieved the state-of-the-art on a BTCV public leaderboard for the task of multi-organ semantic segmentation, and also we showed competitive performance on spleen and brain segmentation tasks using the MSC dataset. And we think that our model actually paves the way for a new class of transformer-based networks for medical image segmentation. So going away from the current CNN-based approaches to the transformer, I think we have already initiated that. So UNETR is already available as part of MONAI. Also, we have added 2 tutorials for multi-organ segmentation, and we think that these resources should help researchers to get to know our model and be able to apply that to their desired applications. We also have a dedicated repository on the MONAI research contributions, so feel free to also check that out. And I think all of these resources should be helpful. So with that being said, I would like to finish my presentation, but I think we can actually have some questions from the audience.
Yeah, so I don't see any questions currently right now. We did link the original paper into the Discord chat. So definitely take a look at that. I think, Ali, that there's another paper that's being reviewed right now that's sort of an update to the original paper. But you can go through, take a look at the paper. It's there and available. What I might suggest is, if you wait around, Ali, we have one more lightning talk here from Annika in just a second. And if there's any other questions that come in at the end of both of the lightning talks, then we can kind of answer them at the very end. And so stick around for another 10 minutes or so, and then we can kind of see if there's any other questions that come up. Or feel free to go to the Discord chat as well and answer anything there as well. But thank you, that was great.
Okay, sure, thanks.
Cool. So as a follow-up, we have another lightning talk here. So we have Annika, and she's going to be giving a talk on a paper called Common Limitations of Performance Metrics in Biomedical Image Analysis. This was a paper that was presented at Middle, and it actually won the Audience Award for Best Short Oral Presentation. So I see, Annika, you're there on webcam. Thanks for joining. And so feel free to give yourself a longer introduction, let us know what you do, and then go ahead and take over the screen and start sharing for your presentation.
Sure, thank you. So I think I start sharing, so make sure that everything works. Okay, great. My name is Annika, and we are working on validation actually, and want to bring forward also metrics and guide people on how to actually best validate your algorithms. So, and this is what this paper is all about. And I will give you an introduction of how we're actually aiming to do this. So let's get started. Okay, now it is. So when you build your model, when you develop a new model, then you first start with the architecture, you train your model, you validate your model, and you then continue to do everything again. And all these steps go hand in hand. But the model validation step is often a bit underrated, which is a pity because it's a very important step of the cycle. But it's also not straightforward. So if you want to validate, then you have to choose specific performance metrics from this huge pool of measures. And it's definitely not easy to see which one to choose, because every of these metrics has specific strengths and weaknesses, and you have to know about them to choose the right metric for your specific task. Let's consider an example. So let's say you want to classify patients into sick and healthy classes, but your data set is highly imbalanced. So you have only very rare cases of the healthy class. In this case, you shouldn't use a metric like the accuracy, because this metric is not designed to handle imbalanced data sets. And it just not covers that you're actually doing a majority vote, like in this example. For segmentation, the most commonly used metric is the dissimilarity coefficient, but it also has some limitations. For example, here you see one case in which you want to segment a very tiny structure, such as the brain lesion. And for this, a single pixel difference will already lead to a huge change in the metric values. And this is often not desired, especially if you have many different shapes of different sizes. So these and other limitations are known in the literature, but researchers are still requesting for guidelines on how to choose the best metric for a specific problem. And we decided to aim for best practice recommendations for metrics in biomedical image analysis. We're doing this with the Delphi process. This works like this. We have a small group of Delphi coordinators. They are designing a set of questionnaires which are then transferred to a Delphi expert panels. And here we have researchers from all over the world, from different institutions worldwide. Their feedback is then going back to the Delphi coordinators. They're evaluating everything, and then they're doing another round of questionnaires. And with this iterative nature, we're coming to a consensus decision on these best practice recommendations. So you know that the world of image analysis is just huge. There are so many different applications, and therefore we decided we have to start somewhere. And we wanted to start with problems that can be interpreted as classification. For example, image level classification, but also things like object detection, in which we're categorizing different objects, or segmentation, in which we're categorizing a single pixels into different classes. So how does it look like? We're starting with the driving biomedical question, the actual problem that we want to tackle, because this is very important to decide what we actually want to do. Then we continue with a task mapping that brings you from this question to the correct image processing task from the 4 tasks I just presented. And this may sound straightforward, but it's definitely not, and it's often done wrong, and then you use incorrect metrics, and your validation is not really telling you the right thing. Therefore, we have this mapping. Then you have the right task. Each task has a dedicated metric pool, which also comes from the expert panel. And then we use a metric mapping, which brings you to a set of metric recommendations based on the task and the biomedical question. So the first thing is then to choose the right task. And we designed it in form of a flowchart, which asks you different questions, which will lead you to the correct task. For example, is your problem global or local? Are you interested in pixels or objects? All these things are asked, and then you're hopefully landing somewhere over here, identified the right task. So from there, we want to choose the right metrics. But this is still dependent on the driving biomedical question, because each problem has specific characteristics that are important. For example, for segmenting medical instruments. You have to know they have different sizes and shapes. All of these things are important, and therefore you have to choose your metrics carefully. And metrics like the DICE or the IAU is just not designed to handle these different things, as we showed in the example before. For other real-time validation problems, you need metrics that can be computed quite fast. So you also need to consider the compute time and memory consumption and all these things. So we're currently looking at all these problem characteristics and assigning them to different scenarios. When you validate your algorithm, in the best case, you shouldn't use just one metric, but combine different metrics that cover different aspects. But many metrics are very similar and often used together for validation, which is not good because they're not really adding additional value to the validation. And therefore, we are currently working on such a metrics as you see here. And this is telling us which metrics are closely related. For example, you see here, the F1 score and the IOU are very similar metrics. So we mark them in yellow. And you shouldn't use both of them for validation, just choose one over the other. And with this, we want to cluster metrics and say, well, choose one metric from this cluster and one metric from the other cluster. Makes it easier for you to find the right metric. So we're not at the end of the Delphi process, so unfortunately I cannot present you a full set of recommendations, but we're currently going for this. We're collecting common scenarios from the biomedical image analysis domain, for example, instant segmentation of medical instruments for endoscopic data. And for these, we're providing recommendations with a pro and con list for different metrics and explanation why you choose one or the other. And with this, we hope to cover many different use cases, but we're also covering some corner case scenarios. Another thing that we're working on is the exact limitations of metrics. And here we have a dynamic preprint. So a preprint that's updated when we collect more limitations. And we present the limitations in form of pictures, graphical illustrations of the different strengths and weaknesses of different metrics. The current version only focuses on segmentation. for example, visualizing shape unawareness of the dice metric. So all of these shapes lead to the same dice value, although they look quite different, or the effect of mathematically related metrics. And we're currently working on extending it to classification and detection. And if you want to look at it and know some other important limitations, we're always happy to give a co-authorship to substantial contributions. And finally, we also wrote a blog post about it on a bit, with different applications, a bit more focusing on classification also, and also other things like how to aggregate metrics when you have a hierarchical structure of data. All these things are also covered in this blog post article. Yeah, with this, I would like to thank you for listening and my team and collaborators, and I'm happy to answer any questions.
Great. Thank you, Annika. It looks like there is one in here, and I think you kind of alluded to it there at the end of your presentation, but someone asked, how can we use these recommendations, and if it will be released as a tool publicly usable? So if there's any links that you also have available, I know you're in Discord as well, so definitely feel free to link them in there so people can check them out. I don't actually have the links available. But yeah. So what I'll probably recommend is, it took a little bit for the UNETR questions to come in. So Annika, if you want to stick around for another few minutes, we'll go through and maybe we can get Ali back on to answer some of the UNETR ones. And then hopefully we'll have some more questions come in on your topic, Annika. So let me go through and I'll unmute Ali again or see if he, let's see.
Thanks, Michael. Sure. So there are some questions from the audience. If you don't mind, I just share my screen again.
Sure. Yeah. And you can go through. It looks like there's at least 3 or 4 there in Discord.
Yes. So most of the questions are about the repository. So I already actually pasted the links, but just to explain. So you can see my screen, correct?
We see you. I don't see your screen actually right now.
Okay. Let's just try this again.
There we go.
Okay, so yeah, I already posted the links here, but we already have basically a complete tutorial that walks you through the steps for basically reproducing what we had for the multi-organ segmentation, the type of the transforms, the loss functions, everything that one may need to reproduce these results. So I definitely recommend you guys to check it out. Also, we have so UNETR repository in the research contributions. So just feel free to check this one out. So some specific questions from the audience, I think, so let's go one by one. So Hirishi is asking if we have any plan to further improve the inference time and what are the strategies. So thanks, Hirishi, for the questions. I think it's a very important topic. Right now we are looking at some techniques such as including a sparse attention or some pruning methodologies that allows you to achieve the same performance in the transformer encoder, basically, but by running it faster and more efficient. So that's actually a future topic of research that our team is also looking at. There are some other questions about the availability of the pre-trained weights. So we will release, so we already have pre-trained weights for these models, but we will release them maybe like very soon, but there are no pre-trained weights right now out there, but basically we have the plan to release them. Also about the paper, so the paper is actually on archive right now, so there is one version here, but we will also publicly release the final version on the archive very soon. So the results of the BTCV is not in this version, but will be released very soon. So let's see, any other questions? So yeah, so the pre-trained weights was from the Serini, so thank you for your question. And also I think we answered all of the questions here. Is there any other questions about the UNETR before we move on?
Let's see. So there was some in the lecture questions. Let me go through and try to find which one. So, well, with whether there's a pre-trained model. Someone asked, do you provide any explanations about the decisions? Did you test with any XAI methods or look at intermediate results?
No, we have not actually looked at those methods. Could also be another interesting direction. Thanks for the question. Yes, we have not yet explored that area.
Yeah, let's see. There is, since you are decomposing into 3D patches, can you do random affine transforms that would typically not make sense if you were dealing with the entire 3D volume? For example, rotating a heart 180 degrees so the aorta is facing down towards the feet in coronal view.
Yes, that's a very good question. So once you actually extract the patches, so you can just use the readily available transforms in the MONAI, as we do also for some additional augmentation, to apply those to the extracted patches. So maybe that's one advantage of the model, which actually works on a patch level, which UNETR does.
Yeah. So another one was whether it would be adaptable to 2D images easily.
For sure. So our model actually also has a 2D version or implementation in MONAI. So what you need to do is to actually set the spatial dimension correctly to be able to use it for your 2D applications. So in the paper, we did not explore that direction, but it will come out maybe later. We will post some tutorial about a 2D segmentation application, but for sure, it can also be applied to 2D segmentation applications as well. Also, I want to mention one more thing. So UNETR uses a VIT or VIT backbone as a transformer encoder. That's also available as a separate module in MONAI. So if you want to just use that for classification, you can also utilize that as well. So I just want to bring that up. So you don't have to stick with the UNETR always.
Great. There's a few more here, I think another 2 or 3. So how does UNETR perform for the segmentation or detection of very small abnormalities, lesions? Did you perform any experiments about that?
Well, that's also another great question. I hope I can actually show the slides back on, but we showed that for very small organs, actually our model performs better than NN unit and trans unit. So a good example of that is the adrenal glands in the BTCV dataset. So we can see that it's entirely captured by our model. And I think that also another good thing to mention here is that because we can capture the long-range spatial dependencies as opposed to CNNs with a limited kernel size, then we can also better segment objects that are extended throughout the entire image. So you can also think that that's also another advantage that transformer models bring in as opposed to CNN-based models.
Great. So there was one here that said there was lots of examples on how to train UNETR, but they couldn't find an example of how to use the trained model to make a prediction. For example, how to save the output the correct way to have an output with the same properties as the input. Does the tutorial that we have go through that? Do you want to show that off?
Yeah, so here I think we briefly show something about saving the model. So once you create the model, I think here we just save the best model on the validation set, right? And then, so since you're here saving the state dict, so with the same token, you can also just use basically torch.load and load this state dict explicitly. But it's a good suggestion. Maybe we can also add another tutorial, maybe as an inference for saved model or pre-trained model. But yeah. I think right now, if you go through this, it should also be available to do it. I don't see any difficulties with that.
Okay. Yeah, so then definitely check out the tutorial that is there in the repo. And then one last question that I see here would be, how large is the data set we need to train for this UNETR, for that transformer model? What sort of data set?
Another great question. So for the BTCV data set, so I think we also have like some basically explanation of what we used, right? So this BTCV data set is actually a very small data set. So 24 samples or so. So you don't need a larger data set than a CNN-based model to train this transformer model. So it worked pretty nicely for us in this application. I think we also applied that to a spleen segmentation, which is also a very small data set on the MSD. We also outperformed a state-of-the-art CNN-based model. So typically it's not a data hungry methodology.
Okay, and then I think actually one more came in. So is it usable with echo image key point detection, or is that possible with sort of a transfer learning approach or a vanilla approach?
Well, so these are all the downstream tasks, right? So I think for your application, I would suggest to just take the transformer encoder of the UNETR, which is just a wheat model, and then try to use your specific detection heads on top of that. I think there are already some works, such as the work by Facebook called a DETR model. So I think all of those approaches should be readily actually available or applicable to this scenario. And if you're talking about the 2D applications, you should also be able to utilize the original wheat model weights. So those are like some pre-trained weights. So then the transfer learning makes sense in that respect. But bear in mind that going from natural images to your application of interest, so there is like some sort of a domain gap. But our experiments show that for 2D applications, at least, starting from like a pre-trained checkpoint always helps to get better results by at least 3 to 5%. We tried that for some applications in 2D, but have not published those models.
Great, and then I guess we'll finish with one more question for UNETR, which is, are there any pre-trained models available for it?
Yes, again, that's a great question. Not yet, but very soon. Stay tuned on that. We will make some announcement to how to basically use pre-trained weights for using UNETR in the MONAI framework.
Great. I think I got through all the questions. If not, we might be able to ping Ali on Discord, and he might be able to answer some things if you come up with some other questions. But great, thanks, Ali. And then Annika, I think that there are a few questions that came in. So I think you answered most of them in chat already, but I think people were wanting to know sort of that matrix that you showed off in your presentation, where to get access to that, when the paper is coming out. Generally, if you just want to talk through, but I know you already answered them there, but kind of recover some of those questions you already answered in chat.
Sure. I mean, we're still working on it, so we don't have the concrete list of recommendations. We don't have the full metrics. I posted the one that we currently have in the chat, so with also the formulas. So it's not straightforward to get everything together, and it always takes some time to get all the huge number of experts together. So we're aiming for submitting in November, December. And I think we will have an archived version of this ready with the recommendations and all of it ready. Yeah, so great. I think the metrics will be huge when we include it. Let's see how it goes out for the paper. Yeah,
definitely. And for people who want to have these links available, we're going to be writing a follow-up blog post, and we'll include the links to the papers and the Medium blog that Annika posted there in chat. So you can always read that up as a follow-up later on. We'll probably send that out sometime next week. And then, yeah, if you have any other questions, people are available through Discord, so feel free to ask them in there. You can also tag people to make sure that they kind of might see a question. So if you have a question for Annika or Ali, feel free to send those out in Discord, but we'll move on with our next section. So thank you too for presenting. Hopefully that was really insightful and helpful for the community, and you guys enjoyed that, and then we can move on to our next presentation. So thanks, Annika.